So this question is related to non-ideal reactors. So in this question, the exit distribution of the non-ideal flow reactors is given in the figure. So the E curve representation is given, and a first order liquid phase reaction with rate constant K. This is given data. K is given. It is 0.2 minute inverse. Is carried out in the reactor, and the inlet concentration Ca0 is given as 2 mole per liter. 2 mole per liter, and the reactant concentration in the exit stream. So in the exit stream Ca we need to calculate. So first what we need to do is we need to calculate what is this E curve maximum value. Maximum value we need to find out. So this I am assuming as it is E max. So since it is in the form of a rectangle, so as we already know, the area under the E curve should be equal to 1. That is nothing but the mathematical representation is integral 0 to infinity E of t dt is equal to 1. So it is nothing but, so since it is a rectangle, it is length into breadth is equal to 1. So here the length is, so height it is E max multiplied by breadth is 2 units, 2 minutes time, this is equal to 1. So then I can get the E max value as 1 by 2, that is nothing but 0.5. So now I got this representation for the E max as 0.5. So now in order to calculate the reactant concentration at the outlet, so as per the segregation model, Ca bar by Ca0, mean concentration at the outlet Ca bar by Ca0, it is given by integral 0 to infinity Ca by Ca0 of the element, each element spent inside the reactor, that is multiplied by E of t into dt. So this is the representation for the calculating the mean concentration at the outlet of the reactor. So for the, since it is given first order reaction, and this Ca by Ca0 of element, this should be is equal to e power minus kt. So this is the correlation for the first order reaction. So now if I substitute in the above equation, Ca bar by Ca0 is equal to integral, so it is varying from 3 to 5, integral term it is varying from 3 to 5 because the time it is varying from 3 to 5. Whatever we collected the exit distribution, so that is in between the time 3 to 5 minutes. So I am going to integrate in between 3 to 5, that is Ca by Ca0 elemental is e power minus kt multiplied by, so here your E of t curve is, it is constant, this is your E of t constant value, that is E max value, that is multiplied by 0.5 into dt. This is equal to Ca bar by Ca0 is equal to 0.5 multiplied by, so integral of e power minus kt is nothing but e power minus kt divided by minus k over the limits 3 to 5. So now I will simplify this. Ca bar by Ca0 is equal to, so I will take out the constant k value, rate constant k, that value is given as, rate constant k value is given as 0.2. so it is nothing but 0.5 divided by 0.2 and then e power minus 0.2 into t over the limits 3 to 5. This is equal to, so if I solve this, if I solve this by applying the limits, then I will get Ca bar by Ca0 is equal to 0.45. So this is the concentration, mean concentration at the outlet Ca bar by Ca0. This is implies Ca bar is equal to, that is concentration at the outlet is equal to 0.45 multiplied by, so initial concentration is given as 2 mole per liter, so it is multiplied by 2, this is equal to, it is 0.9. so concentration Ca bar is nothing but 0.9 mole per liter. So this is your answer. So initial concentration is 2 mole per liter, whereas the final concentration is 0.9 mole per liter. So that even we can calculate conversion also. What is the mean conversion at the outlet of the reactor is XA bar is equal to 1 minus CA bar by CA naught. This is equal to 1 minus, so CA bar by CA naught is given as 0.45. This is nothing but around 55% is the mean conversion at the outlet of the reactor with this RTD data. So whatever based on this RTD data, so the mean conversion at the outlet of the reactor is 55%.